Almost ready. I love when everyone goes silent about me having to tell you what to do. It's great. Like exactly on the hour, everyone goes silent. You guys are so well trained. It's almost Pavlovian. It's bizarre. All right, we are online. YouTube. Hey, it's everybody. Hi on YouTube. Let's see who's. Anybody watching? No one's watching right now. But some will watch later, and I'll slap advertising on it, so I'll make like 25 cents from today. All right. Okay, so fast lecture today because I'm in favor of getting to the point, getting you out of here as quickly as possible, unless we get bogged down with questions and things like that. And it's not because stats are boring. Stats aren't necessarily boring, but they often are. And so we try to minimize the potential boring content. No problem. Okay, so last time we covered the first aspect of bivariate analysis. Bivariation just means an association between two variables. And there are lots of ways of associating two variables. And we looked at two very common measurements of association. That's relative risk and odds ratios. And we looked at methods of digging a little more deeply into those measurements of association, particularly absolute risk reduction and relative risk reduction. So we're going to go a little further today and move on to correlation, which I think most of you have seen before in high school. Have you seen correlation before? Okay, some have and some haven't. Good. So for some of you it'll be review, and for others it'll be relatively new. And my philosophy in this class is I'm not too bogged down on the mechanics, the specific plugging these numbers into these equations to get these answers. It's more interpreting what they mean. So in the case of the Pearson's correlation coefficient, which we'll see today, I will not be asking you to compute it manually. Because why? We have computers. We have calculators. Why bother testing your ability to plug this into that equation? Right? So, however, in the second half of the course, we will do another kind of correlation, the Spearman's rank correlation, in which I will be asking you to manually compute it, because at a certain point, I got to ask you to do some math, right? So that's a somewhat easier formula. So first, let's review a little bit of what we talked about last time. Let's all stare at the latecomers and embarrass them. Wave a YouTube wave. Hey, you know, there we go. Got a wave. Here, okay. They're the latecomers. We shame them. Okay, so we looked at the relative risk, which is the granddaddy, or the preferred measurement of association when we look at epidemiological or population health risks. So if you read any sort of media report on whether or not this thing in the environment is affecting that, usually they try to report relative risks. Well, the journalists won't report it, but usually the scientist they're talking to is reporting a relative risk. And that's because we say the risk of getting this outcome, if you're exposed to this thing, is greater than if you weren't exposed to it, with the understanding that even if you weren't exposed to something, your chances of getting the disease is not zero. There's always some chance, even if you haven't got the outcome. For example, if you don't smoke, you still have a chance of getting lung cancer, right? But if you do smoke, your risk of getting it is greater, relatively. So the odds ratio, on the other hand, we use to estimate the relative risk, and we use it because why? Remember why we use it to estimate the relative risk? When do we do that? Who paid attention last time? Yes, sir.
Is it in case control study?
Okay, why is that? That's correct. Okay, you got half the answer. That's right. Do you remember? Why in the case control studies we prefer odds ratios to relative risks? I see only one person was halfway paying attention. Let's see how this works. So that's because a relative risk is the ratio of incidence rates, and a case control study can't measure an incidence rate. It's a subtle nuance. We won't go too deeply into that beyond that particular observation. When you get to epidemiology later on, we'll explore that that phenomenon more deeply. Just remember, an incidence rate is what happens when we move forward in time. Right now, between now and this afternoon, how many of you will get a sniffle? That's an incidence rate, right? But if I choose people with sniffles, I look backwards to see how many of you stayed up late. I can't compute an incidence rate because I selected the sniffly ones. So we use an odds ratio to estimate a relative risk, and it's only really relevant when our disease is somewhat rare. Okay. So I want to say something about absolute measures versus relative measures, and this is an important little nuance when we look at measurements of disease states in populations. So an absolute measure is not relative to anything else. It's just a number. For example, number of children, number of cases, your age, etc., your weight. This is an absolute number. I measure it, that's what it is. A relative measure is a ratio or a rate or something relative to something else. So the number of number of cases per 1,000 people, that would be a ratio. A rate, technically, is when the denominator has a measurement of time. So an incidence rate would be the number of cases per population per year, right? That's just a etymological grammar Nazi sort of observation. I wouldn't worry too much about that. The important part here is relative versus absolute measures. Number of children per family, that's a relative measure because I have a denominator there, family, and so forth. Why is that important? Well, here's an example. Here's a fake example, and I'll give you a real example. From 1994 to 1995, the prevalence of dumbass disease in Loserville increased by 300%. There's an epidemic of dumbass disease in Loserville. That's amazing. What's going on in Loserville? But actually we went from 1 case to 4 cases, right? That's a 300% increase. But is that a serious number, 1 case? No, it's not. I'll give you a real example. In Ontario in the 90s, the number of cholera cases doubled 1 year. It doubled. The media went crazy. It turned out we went from 2 cases to 4 cases, right? That's not a lot. And there are probably people who went to Colombia for the weekend and came back and, oh, I got cholera. Right, so the number of cases is an absolute measure, but the proportion increase, that's a relative measure. So which one we choose depends on the question that we're asking. It depends on the kind of wisdom we're trying to extract from the situation. So a relative or absolute measure can be misleading depending on the situation. You have to choose carefully. Here is a textbook example, which is not as fun as my examples. Here we have 2 scenarios. It doesn't matter what they are. Let's say they're, I don't know, smoking and lung cancer. In this case, the absolute risk in the exposed group is 0.2. The absolute risk in the, that should be non-exposed. Anyway, this should be non-exposed, that should be non-exposed. So the absolute risk in the non-exposed group is 0.1, and so the relative risk is 2, and here it's 0.6 and 0.3. The relative risk is exactly the same, but in this case, both groups have heightened exposure rate, heightened outcome rates, right? That's epidemiologically interesting, that in both of these groups here, the proportion of people getting our outcome is quite high, just that relatively it's not, difference is not, there is no difference. I'm waking up here. All right, so that is not as clear an example as my fake examples. Okay, so focus on my fake example. Loserville, dumbass disease. Absolute measure, relative measure. Okay, so moving on to correlation. Can I move on? Are we clear on absolute versus relative? Excellent. So correlation is one of those fun words that I always misspell. It's got 2 R's. I always forget that because I'm thinking it's co-relational. It's relation and co. There's an extra R, so it's relation and core. It makes no sense to me. So it's got 2 R's. It always freaks me out. A correlation is just a bond between two measurements. That's the definition in language. Mathematically, it's the association between 2 continuous variables. And the nature of the continuous variables dictate the kind of correlation we can compute. So if it's integral or ratio, we'll do the one that we're looking at today, which is Pearson's correlation. And if it's ordinal, then we'll do one later on in the semester called Spearman's correlation. But in general, if we have 2 continuous variables, we want to see if this one increases, does the other one increase? Now, if this one decreases, does the other one decrease as well? I say nothing about how they're related, the mechanism. whether or not there's a causal relationship or some kind of intimate machinery that causes one to change. It could be entirely spurious. I'm just saying that I observe that as one increases, the other one also increases, and as one decreases, the other one also decreases, or vice versa. To explore correlation, we look at this thing called the scatter plot. And the scatter plot is the most intuitive of the graphs that you'll encounter. The first thing you ever graphed when you were a kid in grade school was probably a scatter plot. And all it is one variable on the x-axis and the other variable on the y-axis. And a scatter plot looks at how linear-ish my data is. It looks at more than that, but in the example today, we're looking at linearity, how much of a straight line it appears to be. And for the scatter plot, we can look at the direction of that relationship. Is it going up? Is it going down? And how tight it is. So the tightness is our magnitude, and the slopishness is our direction. So here we go. Here's an example of time and distance. So if you're in a car moving at a constant velocity, so every unit of time, you go the same unit distance. So I go 2 hours, I travel this far, another hour that far, another hour that far, and the relationship is pretty much a straight line. That's the nature of zero acceleration, is the relationship between time and distance is constant, therefore it's a straight line. So that would be the classic straight line correlation. So we say that if it's going up like that, that's a positive relationship. It's going down like that, that's a negative relationship. So bottom left to top right is positive. Top left to bottom right is a negative. Okay? So this is what we call a perfect linear relationship. It's perfect because it is a perfect straight line, meaning that for every value of x, I can perfectly predict what the value of y will be. And you did this in, I think, grade 10 math, probably, when you look at straight lines. So I remember, I'm such a math dork. I remember when I was like learning straight line equation for the first time, y equals mx plus b. Such a drama queen. I actually had, I've seen the face of God. Because to me it was magical. You can constrain a set of infinite points to behave in a straight line by writing a sentence. That's magic. That's amazing. So maybe you don't feel the same way, but appreciate that's pretty magical, that we can describe and predict perfectly the behaviors of points in the universe on a Cartesian plane. That's magical to me. Okay, so this would be a negative relationship because top left to bottom right, and this is a perfect negative relationship, meaning it's a perfect straight line. Okay? So later on in the semester, we'll also do straight line modeling, and we'll return to these concepts later on. So look at these data points here. They're tightly packed, but you can still see that there's a linearity here. Right? So if your eyeball is, oh, it's like a straight line. Okay, and this is where the quality of the human animal comes into play. You look at this one, is there a straight line there? Some would say yes, some would say no. I see something going down over here, that way. If we were to put if a point were to appear somewhere, if you had one outlier, well, would you still see a straight line, or maybe, maybe not? Right? So the qualitative nature of the human gaze comes into play. Is there actually a relationship going on here? So we try to develop indices to apply a quantitative measure to determine if, in fact, there is truly a relationship, or is it just a random scatter. I would say there's truly a relationship here, but not a strong one. I think we all agree there's a relationship there, relatively strong. Okay, so the strength of the relationship is the degree to which it is tightly packed and somewhat linear, and the weakness of it is if it's more dispersed. Now, these slides, these are made by the textbook manufacturer. They say strength is related to linearity. I'm hesitant to say that because there are different kinds of relationship we tend to look at with scatter plots. It doesn't have to be a straight line. It could be a curvilinear line, we call that, where it kind of curves a bit. It could be an atonic relationship or things like that, or a parabolic relationship. All kinds of possible relationships exist here. Did you ever do Fourier transforms or power series in high school math? Anybody do Fourier? Nobody? Power series? Okay. We won't go into that. I'll mention it again when we do line modeling. But the idea of a Fourier transform or a power series analysis is it's possible for any bunch of data you give me for me to devise an equation that describes them perfectly. It's possible using a Fourier transform or a power series transform, right? And the degree to which that is useful depends on the story I'm trying to tell. So here, for example, I think we can all agree we can probably fit a straight line here, either by eyeballing it or by using our methods later on in the semester where we actually compute what a straight line would look like, right? It's also possible for me to plot a perfect curve through every single point using a Fourier transform. It would look insane. It would look like y equals x sine 12 pi x over 3 squared divided by your mother, right? It would be really insane. And the degree to which that is useful is debatable. So the struggle is always the simplicity of the model versus the degree to which the model reflects the data at hand. Because ultimately, when we collect these data, we're trying to describe the real world. So these data may or may not be representative of the real world. The more carefully I model it, the less likely it is representative of the real world. Did I over-describe that? Do you get what I'm trying to say? Maybe? Okay, you're looking kind of bored. I'll move on. All right. So here we have this. I think we all agree there's nothing going on here. There's no relationship whatsoever. Maybe someone sees something. I don't. And that's a challenge. Somebody might see this, maybe have a more creative mind than I do. And then you have to struggle to find some way of mathematically describing what's happening over here. And this one is, what do you see here? You see a straight line here? Yeah? You see it like, most people see it like this, probably, right? I see two lines, one this way and one that way. This would be a curvilinear line. There's a curvy portion and a straight portion. But it's possible for us to map one straight line here, one straight line there, or one straight line down the middle. Which one do we do? It depends on the theory we're trying to explore. If we know that this is a car moving at a constant velocity, it's probably a straight line. If this is actually like, I don't know, a comet moving through the solar system, it's being influenced by a variety of gravitational forces. Maybe at some point it changes direction due to some gravitational force over here. In that case, I know there's going to be two events happening. So we have to make sure that our data doesn't speak for itself. It is informed by the context from which it is derived. So this is why computers can be great. They get smarter all the time. The ability to process data is great, but the computer doesn't understand the context. So the human animal must always be present to fit the appropriate path. All right. This is actual data from Old Faithful. This is the geyser in the USA that erupts occasionally. And if you were just to look at the scattering of the eruption duration and the time between the eruptions, you would see two clusters over here. Right? If you were to plot a straight line, you can probably predict, you know, let's say the eruption I'm watching right now is this long in minutes, then I know that probably I have to wait 70 minutes for the next one to start. That's the way this works. But we also see something else. Because of the clustering, we know that there are two general types of eruptions here. They're the ones that are slow duration, slow wait time, and the ones that are high duration, high wait time. And there's nothing much in between. So suddenly, by plotting these data, I've derived two pieces of information from this natural phenomenon. I know that it is predictable, based upon the eruption I'm watching now, how long I have to wait for the next one, but also I know that the eruptions come in two broad categories that I can now explore through geological science to try to explain it. So that's a pretty basic, you know, grade 10 level mathematical analysis I applied. I didn't have to know any complicated stats to do them. Interesting. Now look at that. That's pretty scary, huh? So that's a three-dimensional scatter plot. So let's say we're looking at, I don't know, the wait time for the eruption, the duration of the eruption, and the temperature of the water coming out. Let's say the water temperature is different a lot. We have three axes we can plot, and we have a strange relationship now. What do I do with this? I have no idea. But we can do many things. So one of the last things we'll look at in this semester is, you know, multiple linear regression. That's where we try to predict the outcome of a continuous variable based on several predictive factors. For example, one of my grad students did a project looking at predicting body mass index of women living in Indian slums. So you know what a body mass index is? Okay, right? So, and she used a variety of factors, including their age, their marital status, how many kids they have, their income, whether or not they watch TV. All these factors were modeled to predict an equation such that we can actually predict, in theory, what your BMI is going to be if you have these particular characteristics. That's a very common technique to use to explore the various factors responsible for various important outcomes. Now, you may ask yourself, why would I want to predict your BMI in slum? I don't. That's not why we do it. We do it in order to establish which factors are most important. Because when we do the equation, we will see that BMI is equal to X times your age plus Y times your height plus Z times your income plus this times whatever. And that thing that I multiply those factors by allows me to rank which factors are most predictive of this outcome. So in our thesis, we now know that, in fact, income and social class, and in fact, you have a TV, that's actually a big one, is a very predictive of your BMI in these slums. And we're publishing that right now. So that's a standard multilinear modeling exercise. So that's an example of multivariate analysis. But today, we're doing bivariate analysis. So we're the relationship between two variables, not multiple variables. First example, this is a heart disease versus wine consumption. And I don't know if you're too young to remember this, but in the 80s, this was big news. So this is a number of heart disease deaths per population. This is wine consumed. So each of these dots represents a community. Right? And each community, they looked at the average number of heart disease deaths in a year and the average number of wine glasses consumed. And they found the more wine glasses consumed, the less heart disease deaths they were in that population. This made world news. Drink more wine, less heart attack, yay. But of course, it's a little flawed because you can't control for what else are you eating? Are there genetic factors in these populations? Are these really young populations? Maybe these like college towns. These are retirement towns. We don't know. Okay. So, but in general, there seems to be the trend. And this has led people on the path of, the Mediterranean diet and things like that. It has since been shown that, in fact, yes, there's a compound in the skin of red grapes that, when fermented, does seem to reduce the risk of heart disease. Resveratrol is called. And if you really want to know, the best kind of wine for having a high dose of resveratrol is Pinot Noir. That is why I always drink Pinot Noir. It's the only wine I know, and I sound fancy when I order it. Okay. And here we have, right, so the grouping here is such that it looks like a negative linear relationship. It looks that I can predict if I drink this amount of wine, my risk of heart disease comes down this much. Obviously, it's not as simple as that. But it's certainly compelling. It's the beginning of wisdom. It's not the end of wisdom. So, as you can see, with these, this is random data here. When we have data like this, not everything cooperates. Yeah, these guys appear to having a straight line relationship, but this guy is not cooperating. He's an outlier. We covered outliers already. We defined outliers as a certain number of IQRs away from the bottom number, right? So what do we do with outliers? It's interesting because if I were to plot a straight line here, I would say the line is somewhere over there because the outlier will pull my straight line that way. However, we know that because we don't like that guy, maybe this is, again, heart disease risk and wine consumption. We got like a town of alcoholics over here or something, right? So they're dying a lot and they're drinking a lot. Okay? And so we don't want to include them. Then we know this is the actual relationship. But that outlier is really drawing the conclusions I make from my data to a direction that is not appropriate. So with scatter plots, we can actually right away visually appreciate where the outlier probably is. That's what that's saying. Okay, so what's happening here? Is there a relationship or not? It's hard to say. Okay, it looks like there's nothing going on, right? So if there's a particular this sort of spherical or circular scatter pattern, this would give me a zero correlation. Maybe there is, maybe there isn't. I don't know. There's probably something happening here that can't be described via simple correlation. It's probably a more complicated relationship mathematically. And if I were to rely upon just correlation, I wouldn't get that little bit of a wisdom. So keep in mind correlations are limited. So with scatter plots, we can visually and quite quickly explore the nature of a relationship, looking at the strength of it, and the strength is the tightness of the grouping. The nature of the relationship is the shape. Is it a straight line? Is it a curve? Is it 2 lines? Is it 3 lines? Direction, is it positive? Is it negative? Right? And the presence of outliers. Right away, I can get at least 4 important things when I create a scatter plot. Okay, so there's a scatter plot. All right. So one of the ways that we summarize the data in a scatter plot is with a correlation coefficient. There are lots of different correlation coefficients. All that term means is it's a number we compute to describe the degree of relationship between these 2 continuous variables. And this coefficient usually includes in it some aspect of the direction and some aspect of the strength. All right. So strength is also magnitude, is the word for it. So the one we'll talk about today is called the Pearson's product moment, which is a physics term. Don't worry about that too much. We also call it Pearson's R or Pearson's rho. That's actually a Greek letter rho. If you call it R, that's okay. So I think the textbook says it's P sub R. Most of the stats geeks would say it's rho sub P. I'll probably use both interchangeably because I'm not consistent like that. But keep in mind, I want to keep you distinct between Pearson's coefficient that we'll learn about today and Spearman's that we'll learn about later in the semester. They're very different ideas. So Pearson's is today. So Pearson's is great for interval or ratio level measurements. Spearman's, that we'll learn about later in the semester, is great for ordinal measurements. Having said that, you can probably do Pearson's for ordinal as well. People have done it. It's not the best, but it is possible. So when you interpret a Pearson's correlation coefficient, the number will range from -1 to +1, where 1 or -1 represents a perfect relationship, a perfect straight line. Right? The -1 obviously means a negative relationship. The +1 means a positive relationship, and the 0 means no relationship. The 0 is that random scattering we saw earlier. Right? So the minus sign's negative, plus sign's positive. That's convenient. So the bigger the actual number, the absolute value here, the magnitude, the stronger the relationship. So obviously we're looking for a bigger magnitude all the time. The formula is complicated. I do not ask you to compute it in this class. But if you really want to see it, that's what it looks like. You happy? Right, I guess not. You don't want to do that. So but we use computers to compute Pearson's correlation coefficient. If you really want to try it out, you can do it. So how do we interpret the number? We know that it's always between -1 and +1. And the closer it is to unity in either direction, the closer it is to a perfect straight line. But are there cutoffs to determine what determines a good relationship versus a weak relationship versus a pretty good relationship? Yeah, sort of. There's sort of cutoffs. So here's a summary of the guidelines here. So if our rho, that's a rho, not an R, is 0, then they don't vary together at all. The relationship between the 2 variables doesn't appear to be anything. If it's between 0 and 1, then they're increasing together. If it's between -1 and 0, then they're decreasing. Well, one's decreasing and the other one increases. Okay? And if it's exactly 1 or -1, there's perfect correlation. So what are the cutoffs? Here is one way of looking at it. This is from Wikipedia. Right? We can say that if it's between 0.09 and 0, then there's no correlation. If it's 0.3 to 0.1, it's small. If it's medium, and so forth, right? So this person here in Wikipedia has made these cutoffs. This is from another website. They say that 0 to 0.19 is slight, 0.2 to 0.39 is low, 0.4 to 0.69 is moderate, and so forth, right? And this is another one. -1 and -7 is strong, and so forth. Which one do you use? There is no consensus. So different statisticians like different cutoffs. In general, it's better to report the number rather than to qualitatively, decide on your own whether or not it's good or bad. I like this one. So this is the one that we're going to use in this class. So if I ask you to interpret the quality or the magnitude of a correlation, then use this table here. And note that the same thing applies to negative numbers. This is for the positive side. The same thing applies to the negative side. So if your correlation coefficient is minus 0.21, then you say I have a low, quite small, negative correlation. If it's minus 0.75, I have a high negative correlation. Okay, so we're using this one. Examples from the textbook. So the textbook, you've got a flat tax for every $5 earned. That's a 1. That's a perfect relationship. So how would that look? If I were to graph that, I would see that if on the x-axis would be the amount of money I earn, and the y-axis would be the tax that I pay. If you have a 1 in 5 flat tax, that means every time I go 5 over here, I go 1 up, 5 up, 5 up. It's a straight line. That's 1. Yeah. Here's an example of a no relationship. A nurse's degree of autonomy and height. Is there a relationship between autonomy and height? How do you measure autonomy? I don't know. Do a survey of nurses and you ask them on a scale of 1 to 10, how autonomous do you feel? How much control do you have in your job? And they'll give you a number. And then you also measure them. So you get 1,000 nurses and you figure out, oh, the taller you are, doesn't make a difference, right? Obviously not. No theoretical reason to assume that height is related to autonomy. So there's no relationship. Here we have a diabetic person's knowledge and their age. So older people are somewhat less knowledgeable than younger people. Minus 0.2 relationship. So it's a low correlation and it's negative. So the older you are, the less likely you are to know about diabetes, but it's not a strong relationship. And so forth. We won't go through all of these. So some of the things that affect correlation, range is one of the biggest things. So range of your variables. Remember what range is? What's range again? Really? Yes. Exactly. The difference between your lowest value and highest value in your data set. So the breadth of that range will have an effect on your correlation. Ideally, we like to compare things with similar ranges. It's very rarely the case we have that opportunity. So if I'm comparing age and height, what's the highest possible age you can get in years? In theory. These blank stares. Oldest person I know is 27. In theory, you probably mean someone who's infinitely old, right? In theory. In practice, probably 100, right? What's the highest height you can get? Well, in theory, you can probably someone who's infinitely tall. In practice, probably like 8. So can change the units to make them more reasonable, but theoretically both similar ranges in that they're infinitely high, right? But if I'm computing the correlation between age and how many children you have, well, again, your age probably goes to 100. Remember, kids you can have probably infinite, but likely under 5, right? And so the range of children is quite small, the range of age quite high. Correlation between those two will be problematic. The fact that one of them is so much shorter than the other pushes the correlation coefficient closer to 0. I'm less likely to find a correlation if the ranges are dramatically different, as I'm trying to say. So we don't like that. Sometimes it's unavoidable, but we try to avoid it. Okay? Some things that correlate well. Height and age correlate very well up until your 20s. Why does it stop in your 20s? Stop growing, right? So when you're 5, you're taller than when you're 4. When you're 10, you're taller than when you're 5. When you're 15, you're taller than when you're 10. When you're 20, you're taller than when you're 15. When you're 30, you're not taller than you're 20. When you're 40, you're not taller than when you're 30, right? So it goes up and it flattens out, right? So there we'd have, depending on how long you collect data, the graph may flatten out after time. So education and income, they correlate well. So the more educated you are, technically the more income you make. Height and weight, they correlate well as well. So the taller you are, the heavier you are. And really that keeps on going up. So if you're 20 feet tall, you're probably really, really heavy. And so forth. So here's some examples of scatter plots and coefficients. Here's an example of a perfect negative correlation. Here's an example of nearly perfect positive correlation. It's almost 1. This is 0 correlation, and this is, that's one we looked at earlier. Right? So look at this. This is a famous example. In a New England town, the number of shark attacks per month were plotted against the number of ice cream cones sold that month. And they found that, in fact, it's almost this is real data, by the way. This is almost a perfect correlation. So it was reported that, in fact, ice cream sales cause shark attacks. Okay, is that true? What's actually happening here? Yeah?
There's just more people.
More people?
Like, the more people that buy ice cream, there's more there.
And why are they there? You're right, why are they there?
Like summer?
Summer, exactly. So heat. So we say there's a confounding influence of temperature. On hotter days, you're more likely to be at the beach, and you're more likely to buy ice cream. So that's what's happening here. All right, so in other words, what I'm trying to say is correlation is not causation. You've heard that mantra before, right? It's a funny joke. I'll read it out loud. You can read it out. But people often forget it still. And we always publish correlation statistics because they're fun. And we try to sort of cache our language to imply causation, when in fact it very rarely is the case. So, in other words, a correlation between variables never implies that one caused the other. There is some kind of link, but it's not necessarily a causal link. In the case of ice cream and shark attacks, there was a link. The link was through temperature. It's a causal thing. Now, when we compute a correlation coefficient, there's something magical about it. If I square that number, if I take the square of my R, I get a really important number. I get the percentage variation in one variable that is probably explained by the other. For example, if I compute the correlation between height and weight, and I get 0.6, a Pearson's rho of 0.6, and I square that, then I can say that 36%, 0.6 squared, of the variation in weight is accounted for by height. Okay. What's the remaining 64%? Everything else. Nutrition, income, genetics, bone density, I don't know, whatever it might be. But we say that according to this small statistic, 36% is explained by that one thing, the one variable we accounted for. This comes into play later on when we look at multiple regression and different variables in the soup. We can compute R squared for the entire thing and say that X percentage of variation in, say, women's BMI is explained by all the variables in my soup. Yes, sir?
How can you get that just by squaring it? What does squaring do?
It gives you the variation. I know what you mean. I know what you mean. How do I get that? That statistically is what it means mathematically. And we interpret it in fashion. It could be wrong still. What I'm saying is the data that I've collected in this area here, how do I explain this? If you look at the Pearson's rho equation, it's explaining changes along a single dimension as one change the other changes. If I flip this to 2 dimensions, i.e. square it, I'm getting a more robust arithmetic explanation for how these numbers are changing. I'm not really explaining the real world. I'm only explaining the degree of change in the numbers. And I'm struggling to explain this, aren't I? I'll think about a better explanation for you next time. How's that? I haven't got the words right now for it. I know what you're getting at, though. It doesn't tell us truth. It tells us the degree of play in these numbers. Okay. Is there another hand back there? No? All right. Okay. So when we compute correlations of several variables simultaneously, like you will in SPSS, we compute a correlational matrix, and the matrix shows us how things relate to each other in one simple way. So here's what our matrix. So let's say I'm computing these variables against each other to see how well they're correlated against each other. Output would be this. Anything along the diagonal is every time a variable is correlated with itself. Obviously, if I correlate age against age, it should be perfect. As you gain 1 year, you gain 1 year, right? And so forth. And if on the matrix should be symmetrical. So A versus B over here should be A versus B over there. C versus B over here should be C versus B over here. So we only report really one half of the matrix. So here, let's say I ask, what's the correlation between B and D? It's over there, 0.17. So the data in this particular data set shows us that only A and B are well correlated, and the rest are quite poor. Right? So that's a visually fast way of looking at how things are correlated. So to do this in SPSS, you go to Analyze, Descriptive, and Crosstabs, and you select the kind of correlation you want. You can select all kinds of risk. You can select correlation over here, and so forth. So your homework is, think about how to answer your question eloquently next time. Remember me, okay? Ask again next question. Any questions? All right, good.